Hi everybody, my name's John Downing and I'm a limnologist and ecologist. And today what I'd like to talk about is the miracles of water. And I know that sounds a little bit hokey, but there are some really special things about water that are important to remember. And it really changes the way that it works as a substance. So I wanted to spend a little bit of extra time on that. My objectives today are, well, here you see a miracle of water down on the lower right hand. When you think of miracle of water, sometimes you think something like walking on water or something like that. But in fact, I just want you to learn about the characteristics of water that make it different from other liquids and make it so special and so fantastic as a medium for supporting life. So we're going to understand the rudiments today of density or specific gravity, specific heat, the heat of vaporization, dielectric constant, surface tension, and absorption of radiation. It all sounds really complicated, but it sure isn't, and I think you'll find it really interesting. At least it certainly will tell you a great deal about how aquatic systems are different from other kinds of ecosystems. Water is a very special substance, and it's important for us to spend a little time thinking about it. Okay, first off, let's talk about the density of water. Here's H2O, and you may recognize this figure from the Calf book. This is how water is structured. It's two hydrogens and an oxygen, and they can, under some circumstances, form sort of a tetrahedral crystalline a structure such as that you see in this image. Now, the density is actually the specific gravity of water, and this is the grams per cubic centimeter kind of measurement. Now, you may have heard this old stupid joke about, what weighs more, a pound of lead or a pound of feathers. And, we're sometimes tempted to say, a pound of lead does. But in fact, because we've called it a pound or a kilo, we call it a kilo of lead, a kilo of feathers. Because we've called it a kilo, we know that the mass is the same. Okay, so they don't have a different weight really, but they do have a different specific gravity. And specific gravity is measured in terms of mass per unit volume, so grams per cubic centimeter. So if you have a very high specific gravity, what it means is you're packing a lot of molecules into a very small space. And if you have a much lower specific gravity, you're packing way fewer molecules or atoms or whatever it is into that same amount of space, that same cubic centimeter space. Now, the density of water is generally about 800 times denser than air. Well, that's really good because that means air sits on top of water, which is helpful. So water tends to be quite dense. Now, usually, the density of almost anything, you probably learned this a long time ago, density of almost anything tends to get higher as the temperature gets lower. It cools and then the molecules get closer and closer and closer together, so the same amount of mass of stuff takes up a smaller volume. Now, if that were true for water, there'd be a problem. And you can do this thought experiment yourself. If you put an ice cube, that's cold water, really cold water, in a glass of water, it floats. Why is that? If it's colder than the water that it's going into, it should in fact sink because it should have a higher density than the water that you've dropped it into. This means that water behaves in a very different way. Now, here's what happens. If you think of a point at about 4 degrees Celsius, to you Fahrenheit people, I'm not sure what that is. Maybe it's about 40 degrees, 42 degrees Fahrenheit, something like that. So as water cools down to that area, it in fact does what you expect it to do. It packs closer and closer and closer together. Then below 4 degrees Celsius, molecules begin to form a lower energy state that leaves a lot of space between them, and that gives them a lower density again instead of continuously higher density. And I can show you this this is a model of sort of the crystallization of water as you go from cold water. Here you see very confused, sort of tightly packed stuff. then you begin to see some forming of crystals, sort of crystalline structure, so you begin to open out the spacing amongst the molecules. And when you do that, then you make a lot of air, or, well, empty space between them, and so you tend to drive the density downward rather than upward. We're going to look at this on a graph to give you some appreciation of it. So this graph over at the right-hand side shows temperature along the x-axis and density, or specific gravity, along the y-axis. What you see is here water behaving kind of in a standard way. As you get it colder and colder, it gets a higher and higher specific gravity as things begin to move together. But when you get to about 4 degrees Celsius, all of a sudden you start forming that sort of lattice work, and the specific gravity tends to decline. Now, you may say that's not very much, but it is enough to form very strong stratification, especially when you would have, say, overlying very warm water. The thing to remember about this means that the highest specific gravity thing is going to be found toward the bottom. And so anytime you have 4 degree water, it should be found at the bottom. So that what that means is sometimes in winter, for example, it's warmer at the bottom in the lake than it is at the top. The top has got ice over it and is sitting at around 0, and so the colder water is, the warmer water is actually toward the bottom. That's a really good thing. It really helps out a lot. And what that does is it allows a lake to not freeze at the top, and allows life to live, organisms to live in lakes over winter, for example. And also it forms thermal refuges for different kinds of organisms, so that there's cool water sort of year-round at the bottom in the temperate zone. Next thing I'd like to talk about is specific heat. Now, specific heat is the amount of energy it takes to raise a temperature 1 degree. And if you're in a hurry to have a cup of tea or something, you sometimes may get pretty impatient at how much energy you've got to pour into that water in order to get the temperature to actually rise. That's the specific heat, that is the amount of heat energy needed to raise a temperature 1 degree, is higher than any other liquid except for liquid ammonia. So it's quite remarkable. It takes a lot of heat to change the temperature. What does that mean? That means that water moderates temperature extremes and modifies local climates, and basically stays at in the autumn, for example, stays at relatively high temperature for quite a long time as the system begins to cool. And even in the summer, it means that temperature extremes are somewhat tempered. If you get a blazing hot day, it doesn't turn the lake all extremely hot and cook the fish that are living in it, for example. The specific heat, very important for moderating temperature extremes. Now, another kind of related idea is the heat of vaporization. This is also called the heat of evaporation. This is the heat input required to turn water to water vapor. And here you see a couple little Bunsen burner diagrams on the right-hand side. Water has one of the highest requirements known. Of heat input in order to change water to water vapor. This means that water, even in the tropics, usually stays somewhere below 30 degrees Celsius because the water can absorb so much heat before it vaporizes. This tends to temper climate extremes around water bodies because they will continue to absorb heat while staying stable in temperature. Now, here's another thing that's special about water, a so-called miracle. It has a very high dielectric constant. This is a capacity of a substance to store charges, and this is related to the ability of any liquid to dissolve and transport substances. In reality, there's almost nothing that isn't soluble to some degree in water. Now, this can be good and this can be bad. What it means is water will pick up contaminants and nutrients and move them along with it. But it also means it can pick up nutrients and allow them to be used by organisms living in those systems so that they can enhance the amount of life they can create. So dielectric constant is quite important. Also, water's dipolar. And because it's dipolar, This makes it an excellent solvent for both salts and polar organic molecules. So basically nearly everything is soluble to some degree in water due to the dielectric constant and its dipolarity. Another aspect that's quite special about water is that its surface tension is very high. Surface tension is a measure of the strength of film at a water surface, and you probably already have seen water striders walking on that. Most spiders can walk right across a calm water surface. But what this also does is it keeps waves from breaking and keeps them from being very choppy, keep the surface from being very choppy, that is having a very high surface area. So the high viscosity and this surface film that forms allows organisms to live at the surface, but it also alters heating and cooling. So it makes water actually act like a gel to very small organisms living in it. So it's sort of like if you were a very tiny plankton organism, water, because of its viscosity, would be very much like living in semi-set gelatin. So you see on the right-hand side just the little contrast of water, but there are more viscous things in the world like honey. But because of this viscosity, it offers good resistance to swimming. And if it weren't for that high viscosity, it would be really difficult to move around in water. So surface tension is high and viscosity is high, and this alters heating and cooling, makes it a good substance for swimming in, and allows organisms to live in the surface film. Its absorption of radiation is really also quite important, and absorption is large and it's small. So absorption means blocking, essentially. So water tends to absorb a large amount of radiation in the infrared, and what this does is it moderates temperature extremes. So it takes up this takes up the energy in the surface water very rapidly and turns it into heat, which then, because of the specific heat, doesn't heat the water very much. It's also very small in absorption, at least in pure water. You see these divers up at the surface, and you're down, way down deep in a very clear system. Maybe you're in Lake Tahoe or Lake Superior or in the Caribbean, very clear water. You can see that there's quite a lot of light penetration, a very great distance, and the small absorbance of light in the photosynthetic region means that plants can grow down there, make a living, and create food for other organisms that live there. On the right-hand side, you see the absorbance spectra of various photosynthetic pigments. You're probably familiar with chlorophyll, various chlorophylls, chlorophyll A, chlorophyll B, and then there are carotenoids. Those are the things that make carrots yellow and stuff. These kinds of various kinds of pigments. So they exist within the visible range, and in clear water anyway, the penetration of light in the visible range is very far, and the absorbance is quite low. So here's a summary of this very short session 3 or module 3. Here's some summary. The density is important because it forms a liquid crystal that achieves maximum density above the freezing point. This is extremely important for the structure of aquatic systems, and it allows overwintering of organisms as well as a cool refuge down in the deeper waters in summertime. The specific heat is very high. That means it takes a large amount of energy to change temperature, so this moderates temperature extremes within the water body. So even though there's a very hot day, it may in fact not heat the water very much. The heat of vaporization is also high. It takes a very large amount of heat to create vaporization, and this means that the maximum temperature in water usually is somewhere below 30 degrees Celsius, and that is a fairly tolerable range for warm water aquatic organisms. Fourth, the dielectric constant is high. The high value makes it an exceptional solvent for salts, and because it's a dipolar, it can dissolve inorganic and polar organic substances. The surface tension is high, and this very high surface tension keeps waves from breaking, thus slowing cooling and heating, and also provides a place for organisms to live at the surface and on the surface. And finally, the absorption of radiation is very important because water absorbs infrared but transmits the light used for plants, moderates temperature extremes, and allows radiation that can be used for photosynthesis to penetrate far enough for aquatic plants to use them.